Hello and welcome. As Margie mentioned, Jeff and I are solution engineers, and though we work with a variety of end users, we support the science and civilian organizations. Today, we're going to be your tour guides reviewing key components and workflows focused around a modern visual scripting environment. We'll give you a high-level overview of ModelBuilder, move on to data engineering and visualization, jump into analysis, and wrap it up with sharing content and models. So with further ado, let's jump right in. I think we're all facing this problem, especially now if many of you are like Jeff and I, balancing work and kids being home and endless meetings. Unfortunately, we still have to address those everyday work challenges that can take up the majority of our day. If I asked which portion of your workflow takes the most time, I bet most of you would say finding the right data, capturing the data, and having the data in the correct format, when all we want to do is get to the analysis. But even that feels like an accomplishment after manually doing the other 4 steps. And we don't even have time to focus on the best way to share content or how the end user will interact with the content. There are environments that help in that department. And in computing, a visual scripting environment lets users create programs or automated workflows by manipulating the elements graphically, rather than by specifying them textually, like Python. Example of these environments include Scratch, a product of MIT, designed for children in K through 12 and after-school programs. Here is a simple graphic and workflow of how a visual scripting environment works, where you have an input, and then a tool or some action occurs based on a variable or parameters. Then you receive the derived results. The visual scripting environment we utilize is ModelBuilder. The input elements are shown in blue ovals. These can be layers, data tables, rasters, features. Then the geoprocessing tools are shown in the yellow squares. These tools are the basic building blocks of your models. Common geoprocessing tools include select, buffer, clip, and intersect. ArcGIS Pro has over 1,000 specialized geoprocessing tools for you to choose from, and all of those are found in those specific toolboxes. And finally, the derived data is shown in green ovals, which is the output from one tool and can be used as an input to another. Some key aspects to keep in mind as we dive into specific workflows. ModelBuilder within ArcGIS Pro is easy to use for those just starting to learn Python or just don't know Python. It displays those visual elements in an easy, digestible manner. It assists in those everyday redundant tasks, whether you're working on data engineering workflows or running analysis. The final aspect I want you to think about is if there are any workflows that you want to just bundle up and pass along to other colleagues. So let's dive into some technical components. ArcGIS Pro is 64-bit multi-threaded, and what that really means is that it enables you to use more memory for your data processing. It's more robust, and the results will be more accurate. The simplified user interface is ribbon-based, where you're only using the tools that you need. That tight integration with ArcGIS Online and Enterprise allows for you to not only utilize the local data, but the data from the web. It's a combined 2D and 3D experience with the ability to have multiple maps and layouts. So think that link and sync situation. The full user experience for this presentation is driven through the Analysis tab or the Geoprocessing pane, where you can search for tools or browse those toolboxes. So for those people that are more familiar with ArcMap, you still have access to that tree view. And ArcGIS Pro supports most tools, models, and Python scripts from ArcMap. The one thing I want to note here is that Arc objects-based custom tools are not supported. There are 4 ways to automate geoprocessing workflows. You can build a model of your workflow using ModelBuilder. Drag and drop tools and data to make a diagram that represents your process. Utilize Python, either a command prompt or run Python scripts straight from the toolbox. Our scripts act in a similar manner as Python and can run straight from the toolbox as well. The last option is via raster functions. If you guess that those are solely for rasters, then you would be correct. We can think of those as similar to ModelBuilder, where you can chain together those geoprocessing tools specifically made for raster analysis. But we're really going to focus today is the first two options, that ModelBuilder portion and those Python. We'll break this down into 6 easy steps. It's important to take a moment to plan out your workflow. Understand the data and the requirements of the analysis you will conduct. Next, create a structure or framework to hold that model. Start to drag and drop tools, pick your parameters. Before running the model, you want to validate to ensure proper syntax, flows, and parameters are correct. Finally, we'll get into running the model. And the best part is that you have the option to run it again or even share it with others. So let's go ahead and jump in to a demonstration of ArcGIS Pro and ModelBuilder. So as we switched over to ArcGIS Pro, you'll immediately notice the user interface. And if you're used to working in ArcMap, it will be a change, but once you get the grasp of the UI, you'll absolutely love it. What you're seeing here is the Map tab. You're going to have access to still like all your main tools that you're familiar with in ArcMap. Here up at the upper right-hand corner, you can notice that I'm logged in with my username as well as into my organization. Just south, I have access to my catalog pane. And then the power here is that this is more project-centric versus that map document individual files and layers centric here. And what that really means is that once I create a new ArcGIS Pro project, I can spin up multiple maps and keep them within my catalog pane, as well as access to those toolboxes. When I spin up that new Pro project, you'll notice that the national parks name in my toolbox comes straight and derived from my Pro project name. And that means it's just created automatically as soon as I spin up a new Pro project there. You can also pull in other toolboxes with script tools and then connect into different databases. Here again, we can notice that we have our national parks geodatabase, but we have also the option to add a database, create a new file geodatabase, as well as to connect into a database connection, like if you had an enterprise or a server. So context and data ingestion is a huge part of understanding your workflow. So let's dive into where we are in the world. I figured since most of us are stuck at home and many of us probably canceled our summer vacations, we'll go and visit Glacier National Park for the main area of interest for this presentation. Glacier National Park was established in 1910 and covers about 1 million acres of land and contains about 25 active glaciers that move due thawing and melting. So what we'll do is go ahead and add a data set. We have options to search through My Content, Groups, your portal, and as well as Living Atlas. So for those concerned about data ingestion and how I get access to it, this is the one main approach that you could take. So we'll go ahead and search all the portal, which means any content out in ArcGIS Online, and type in glaciers for Glacier National Park. You can see based off of my keywords here, it'll show me go and scavenge anything that has those tags and then pull them into my options. We'll navigate to GPN glaciers and then pull that in. So without even running a GP tool or conducting any type of analysis, we get a better understanding of our area and the ecosystems. So let's zoom into one of those glaciers. Each of those colors indicate how those glaciers are receding throughout time. And it's very important to understand those parameters as well as those requirements within that area. because ultimately that affects the habitat, the animal habitats, and the people going to visit or hike in that area. Let's go ahead and jump back out into our full extent, turn off our glaciers, and take a look at some of these other data sets. So what you'll also notice is that there are hiking trails noted in these black dotted lines, as well as the symbology in those pinpoints are the area of interest. So if I'm curious about a different campground or where there's an overlook or a visitor center, I now have them within my map. The white indicates parking areas that I have access to, and the orange, like burnt orange color, is the road access through Glacier National Park. The other point I want to make is that Glacier National Park has an abundant fauna and flora within that area. So we'll turn off our points of interest and take a look at these habitat areas. So the park is home to dozens of mammal species, including mountain goats, wolves, grizzly bears, and wolverines. And over 300 species of birds, including golden eagles, can be found in this park. And that ultimately provides great bird watching opportunities and photography. What we're really going to get into is assessing some bighorn sheep habitat areas. So let's go ahead and jump into our analysis tab. So here in the analysis tab, we have access to our history. So this means that any geoprocessing tool that I run, I have access to add into my model. I can run it again, but we also have the option to schedule it too. So if we go ahead and open, we can go ahead and rerun it as well as schedule. And once we pop up in that schedule, we can take a look at the different settings and times. The other aspect is having access to your Python command prompt. And you'll notice at the bottom of my screen, we have a Python series here, or a Python script here. And then what that is actually doing is taking a feature class and linking it to a REST service and pulling it and converting it into a feature class into my Pro project. There are several other tools available at your fingertips here. So whether you're working with a geoanalytics, so big data, raster analytics, as well as doing predictive analysis, you're able to access those and utilize them either via raster chain function within a model builder or a Python script. So for this workflow, I want to focus on habitat suitability for bighorn sheep. There are a couple of factors that I need to take into consideration. One of those is that bighorn sheep can climb up to elevations of 10,000 feet and typically like elevations of 5,000 to 9,000. So you'll see here that I have an elevation data set that I exported from the USGS 3DEP application. They will stay on slopes of 35 to 80% rise, and the good vegetation that they love and eat is grown on the south to southwest facing slopes. Finally, they feast on shrubs, grassland, and they love to hang out on the cliff and talus slopes. So here I have a land cover classification for all of Glacier National Park. So now that we know what data sets that we need in order to conduct our model, let's actually jump in to creating it. So we can go here into our model, and then we have access to the different properties. I went ahead and already gave it a name. And then the one tip and trick I want to point out is to store tools with relative paths. So that allows you to not necessarily break those links once you do decide to share out the model, do a pro package, and whatnot, so you don't have to actually resource all of those. A couple of other areas I want you to take note of is the environments. So there are 4 different areas in where you can note the different environments for your geoprocessing. So one is at the project level, another is at the analysis level, This one is at the model builder level, but you also have environments within the individual geoprocessing tools. So right now you'll see that my current workspace is the National Parks Geodatabase, and my Scratch workspace is there. So if I have any type of in-memory processing, that's where it's going to be. I can note my coordinate system as well as my processing extent, and it could be as specified below or the same layers. For now, we're going to keep all of these as default. All right, so here at the top, let's take a look at some of those tools that we have access to. We're going to go ahead and start adding some of those. So first and foremost, I know that I need to create a slope. So let's find our slope tool. Double click that and pull that in. We'll also pull in our elevation layer and then make a connect to that particular slope as my input raster. We'll open up our slope tool and you'll notice that it'll automatically pull that input raster. And then here is my output raster space. I am going to go ahead and choose a different database. And I can do that by navigating to my Bighorn Sheep database and then providing a name. So Glacier NP slope. Oh, there we go. And then we have two parameters that we can further refine our tool. So one is the output measurement. So you can do a degree, so a degree of slope. So taking that steepness at each of the cell of those raster surface and then producing that degree. Other is a percent rise. So 30% rise, 50% rise, 100% rise, meaning that the 100 is really steep, right? And then the 0 would be really flat and low. We're going to do percent rise because remember that we want to take a look at the 35 to 80% rise. And our last is the method. So we have two options, planar and geodesic. Planar is if we were to run those calculations on a flat surface. The geodesic is taking an account of the 3D Cartesian coordinate system. We're going to stick with planar for right now. And then this is the Z factor is default. But if you absolutely know that unit, then you can specify that. The other tool we want to utilize is aspect. And that really is going to identify the direction of the downhill slope. So we're going to do it in a different method and go to our analysis tab, click on our tools, and then here you see that we have access to all of our toolboxes, right? So very similar to ArcMap. But we also have the ability to pull in our aspect, and that's as easy as a drag and drop. And again, we're going to make that an input raster. Open this up. You can see that our input raster is the elevation, and then we want to do the same thing as we did previously. Navigate to our Bighorn Sheep. Type in Glacier NP aspect. Hit save, and then we have that option to do planar and geodesic. We're going to stick with planar. So finally, we have to pull in our land cover. So let's pull in our land cover as one of our variables, and then find our raster calculator. And what raster calculator actually does is take into account of all of your parameters or your restrictions or limitations and focuses and narrows down all of those results to give you a binary raster, so zeros and ones. So we can open up our raster calculator and you can see all of these different types of parameters. I like to lengthen this a little bit so I have more space and room to work on. I'm also going to cheat a little bit because I do have a final product here. And the actual MALP algebra that I have to put in is pretty lengthy. So I'm going to go ahead, take all of these, and then copy those and pull those over. It does use map algebra, and you will have to know some SQL in order to conduct this analysis, but once you establish a good flow, you should be good to go. So you can see here that I have my glacier elevation is greater than 5,000, but I also want to take into account of my glacier elevation that's less than 10,000. So anything in between that. Let's intersect that with anything in my aspect that's between these values. And I just know that those values are my south to southwest facing. And I'll show you in the output how you can tell those. Then my slope, let's say greater than and equal to 35, and then as well as less than and equal to 80. And then finally, I have several land cover classes. So I know that the 7, 8, 12, they're all pulling in either dwarf shrubland, grassland, talus, cliff faces, all of those types of things. And then finally, I want to pull in my output. Sheep suitability, and save. So it'll go ahead and check my map algebra, and if it was incorrect, it will give me this big red X here at the top. Click OK, and you see how everything is spread out, but we can fix that. So if we do an auto layout, it'll neatly condense all of that, but also make it a little bit more digestible, because sometimes models can get a little bit crazy. A couple of other things I want to point out before moving on to the results and running it, or at least showing you some of those results, is the tools up here. You'll have access to the different iterators, the utilities, logical, and then more aesthetics of grouping and ungrouping specific model parameters or your model tools there. All right, so it's important to validate. So we'll give a quick validation, and then just to give more of that cooking show method here, because sometimes imagery layers can take a little bit time to run. Let's go jump in to our final results. So if you want to take a look at the output here, this is our original map. And again, we're looking for the bighorn sheep suitability. I want to know, where can I go in these points of interest to, it's going to be my best probability to see these bighorn sheep. This is the aspect that you're going to get. And it's going to be all of this almost clown colors like. But each color notes the way that the hill is facing. So you can see that the gray is flat, then you have north is the red color, and then the south and the southwest are these blues. So that's really what we're aiming for here. The other output is a slope. So let's take a look at this slope. And it's nice, and it's pretty. It gives me goosebumps. I love raster analysis. So let's take a look at some of the textures. So you can see the higher peaks as well as some of the low valleys here. So you can see that this trail follows along this valley. Here's this lake, and then intersects with this road. All right, so we took a look at that. So now, the big finale. Where are these bighorn sheep? So the one thing to keep in mind is that I'm not including all the parameters of bighorn sheep. I could include terrain ruggedness, just the different escape paths and whatnot. So again, I just chose a few variables that I could replicate into this particular model. The purple shows the different areas that I can actually have a higher chance to seeing based off of the parameters that I put in my model of seeing a bighorn sheep. And if I click on here, here's the campground. So maybe I want to camp out there so I can get that beautiful picture that we see on National Geographic of bighorn sheep in Glacier National Park. All right, so I just gave a brief overview of ArcGIS Pro, some of the analytics, as well as how do we start dragging and dropping and playing with those parameters to solve a problem here. So let's go ahead and jump back in to our slides. So what is data engineering? If we break it down, we're focusing on two areas. One is sustaining the data pipeline systems. Think about bringing together 10 to 30 different data technologies. The second is clean and wrangling the data into a usable state, ensuring that the data is clean, reliable, and prepped for whatever is used, whatever the use cases may present themselves. For this first section, we're really focused on the cleaning and wrangling of data. Sustaining data pipeline systems would take the whole hour we have together and even more. Iterators, I believe, are the most important and versatile tools. Imagine if you have several files, data sets, or features that you need to repeat the same process over and over again manually. Instead of choosing that path, you would utilize an iterator that would repeat that process with some degree of automation. And they can really swing in either the data engineering workflows or the analysis workflows. There are a number of iterators in ModelBuilder that you can use for iterating over different values, data sets, and workspaces. So let's take a look at some of these. The for iterator says, I want you to run a number of processes for n times. So that n value can be 6, it could be 10, it could be 100. Some of the others are further down in the list. So I want you to iterate through feature classes, files, rasters, or tables. So you point to that specific location of those files, and it'll just run through all of those in that workspace. So let's break this down. So we have input rasters variable, and that folder contains grids, images, and TIFFs. And in this case, we just want to restrict with a wildcard. So anything that contains the letter A in it, and we want to take a look at any of those grids. The tool has two outputs. One is the raster output as is, connected as an input to another tool. The other is the name variable, which is used in the output name tools as an inline variable. And then finally, that recursive option there determines if the subfolders of the main folder will be iterated through recursively. So we mentioned inline variable, and that really is taking that value or dataset path of that variable and substitute for another by enclosing the substituting variable name in percent signs. And that's called inline variable substitution. There are numerous ways to utilize inline variable substitution. One way is to use the workspace location and utilize that as an inline variable in a project tool parameters. And that you'll enclose the variable name in those percent symbols. So at runtime, you'll actually have the variable value in the C drive, your data, and your geodatabase. And that is substituted for that percent data workspace and percent signs. The other one, which I think is really powerful, is the use of a inline variable substitution with an iterator. So when the iterator to iterate feature classes or raster runs, it creates an output variable for both the path and the name of each of the feature class in that workspace. So the value in that name variable can be used to construct the path to the output projected feature class. So when that tool executes, you're getting that percent name percent, and you're replacing it with the name of the feature class. So you're really just carrying over that name of your original data sets throughout the entire process by using inline variable substitution. Grouping in that model allows you to assemble those processes into logical units. These groups can be collapsed and maximized for visual space or expanded to edit the processes within those groups. There are 5 utilities that support advanced behavior in ModelBuilder. So here is the list of those utilities that you have access to. One of those is collect values. So that's really saying is I have this iterator and I want you to collect or convert any of those lists of the multi-values into a single output. And those values can then be the input into other tools. So like you see here, the merge, the mosaic, the cell statistics. The other one is a select data. So it'll select data within that original data set or that parent element, and then carry that throughout the process. So let's take a look at this. For example, if you are calculating a value in the model, and you want to use the calculate value with the tools, such as a buffer value, you'll also need to know that value, that unique value or the linear unit. So what you'll have to do is, in order to return that linear unit, you have to take a look at that code block along with that distance value, change the data type of the return values as shown in this window, and set that data type parameter to linear units so the results of the expression will be converted to that desired value. So with further ado, let's dive into some data engineering workflows, and I'll pass it over to Jeff.
Thanks, Kristen. I appreciate it. Thanks for everyone for coming to the webinar today. Can you see my screen, Kristen?
I believe, yep, I can see it.
Okay, awesome. So for my portion of the webinar in ModelBuilder today, I want to try to keep it light and fun. We have some pretty cool data sets that I want to show you guys. It's still out in Glacier National Park, which is one of my favorite national parks. We have, like I said, a fun type of data set where we're looking at Bigfoot sightings. And I had to dig pretty deep in the internet to find this specific geodatabase, but you can see that there's some descriptions in here for Bigfoots and things like that. Someone saw a hairy bipedal animal cross trail, items like that. But regardless, Glacier National Park does have a small issue with their parking. As you can see, Glacier National Park is a very large area. I think Kristen mentioned it was about 1 million acres. And there's so few parking spots. So a problem that we're going to solve today using ModelBuilder is, where should you park in order to gain access to your favorite areas of Glacier National Park, or if you want to go to an area where a Bigfoot has been sighted, right? So here's all of our points of interest, and these range from gift shops to boat ramps if you have a boat, items like that. We'll also add back in the trails and roads so you can see how else you can access Glacier National Park. So first thing that we're going to do is we want to find out how far an individual would have to travel in Glacier National Park in order to get to those points of interest. And one of the first things that we have to do is we have to engineer and massage our data to run the analysis that we want to later in the demonstration. So the first thing that we need to do is we're going to create a new model to show you guys how easy it is to do. And one of the first tools that we're going to use is feature to point. And why we're using feature to point is, if we zoom in on our parking lots, you'll notice that they are not points, but they are polygons. And in order to figure out what the linear distance is from our parking lots to our points of interest, you have to convert these to a point, which is why we're using the feature to point tool. We'll go ahead and zoom back out to our full extent. And once those points are created from our polygons, we're going to use a tool that's called Create Teasian Polygons. And so that'll be here. So we'll go ahead and drag and drop in our parking areas. And if you haven't noticed, this is very similar to how ArcMap works, where it's a very drag and drop type of functionality. We're going to input our features. Our output feature class here will be the points in the center of our polygons, which is the parking areas. And from those points, we want to create a Tesian polygon. And essentially a Tesian polygon, if you're not familiar, is essentially an equal area polygon based on multiple features within a related area. So it'll create an equal distant feature class polygon of all of our parking areas. So let's go ahead and run. Well, we'll validate our tool first, and it checked out, so we'll run it. It'll give you a success output warning. I say warning, but it is a success. So we will add this to display. Let's go ahead and zoom back in to ensure that we do have a point within our polygon parking areas, which looks like we do. Zoom back out, and we will add our Tesian polygons to our display. At the display, and you can see these are all equal area polygons based on our parking areas, and it'll make more sense why I decided to do this workflow here in a second. So the next thing that we want to do is we want to create two new fields. Let's go to our model. We want to create two new fields in our point data sets. Here, this is our data engineering group. I know Kristen mentioned that you can group things. It makes it easier for me to visualize my model here. So we have our points of interest and we have our parking lot points. So if you open up the attribute table for our parking lot points, you'll see that there are no XY values in this data set. Now, in order to run our linear distance, you need to add those fields and you need to calculate the geometry attribute. So it's going to look at your coordinate system and add an XY value to each of these feature classes. So I'm doing this both for points of interest and for parking lot points. Do not have to do this for the Bigfoot data because that data set already comes with lat longs. So we'll be using that for our analysis in the analysis portion. So once we run this portion of the data engineering tool, you can see that once we open up the output, you can see that the XYs were created in both of the specific data sets. And this is important to have for when we run our analysis. Okay, and we'll go back to Kristen.
Great, thanks, Jeff. Go ahead and switch over to my screen. All right. So now that we have this data preparation, let's start talking about some of our heart and soul of what ArcGIS has to offer. Analysis allows for you to solve complex location-oriented problems and better understand where and what is occurring in your world. It goes beyond just the mapping component, and it lets you study the characteristics of those places and relationships between them. Our first component is branching or logical tools. Branching is this if and then else condition. So for example, we have a file in a workspace. We create a condition where if that file exists, then add a field. Else, if the file does not, I want to copy and then add a field. There are two branches, if these and then else that. In ModelBuilder, if then else logic can be added via three methods: the set of built-in logical tools, custom Python functions, and then those script tools. Logical tools are a category of ModelBuilder utilities that help you control the flow of processes in a model and enable that if then else branching logic. Here's an example. The field value tool, it checks if the input data has a particular value and an attribute. And we can see here that we have our data element being that input data set, and then we're really just fine tuning and saying, I want to extract that number 5 value. And in this case, it's saying, I want to extract the landslide risk that equals number 5, which is the most critical. And then if that selection exists, I want it to do one process. If it doesn't exist, I want to do something completely different. Script tools allow you to run these scripts from within ArcGIS, using a geoprocessing tool as the interface for the functionality in your script. When you create a script tool, you specify parameters in your script that script needs in order to execute. And those script tools are created within the toolbox. The idea of adding one or more models to a tool within a model is sometimes referred to as a submodel, nested models, or a model within a model. Using one model within another allows for large models to be divided into smaller, more easily manageable models that can be reused. This is also a great way to add more than just one iterator to a model. Here we have a model where it's iterating through feature classes and then collecting values. Then we have our main model, and we can integrate those two by creating that submodel. The utilization of submodels can be simple, or you can get crazy with them, like in this one, where the main model contains 4 submodels that are integrated. A built-in understanding of which processes in your model need to run first so that the dependent processes have data needed to run successfully. This happens automatically as you make those connections using the output of one tool as the input to another. However, occasionally you may need to control the order of operations between the two related but disconnected processes. I kind of think of these as like PEMDAS, what we learned in basic mathematics. A process can be run be made to run after another process by making the output of that first process a precondition to the second process. Any variable can be made a precondition to the tool execution, and any tool can have more than one precondition. So here is an example. We have 2 separate processes. One is creating a file geodatabase and then creating a feature data set. The other is having an input feature, a clip feature, and then producing an output feature class. We can connect those two by creating a precondition. So if I go into my workspace, I create this file geodatabase and this feature data set. If that process happens, I then also want it to kick off the process number 2, where it clips features. Okay, now that we have laid down some of the foundation, let's jump into some analysis workflows. I'm going to pass it over to Jeff.
Thanks, Kristen. I appreciate it.
You
So,
can see the screen.
okay, perfect. So real quick, I want to show you guys how easy it is to save your model. You can save it as here, and we'll just name this T's Poly. That way, if you ever want to use this specific Tesian polygon workflow in the future, you can just pop in all these different parameters and then you're good to go. But on to the analysis portion. Save that. So the first thing that we are going to want to do is do something that's called a spatial join. And we're going to want to spatially join the Tesian polygon layer that we created earlier with the points of interest, the parking area points, and our Bigfoot sightings in Glacier. Essentially what this does is it looks at, here let's zoom in, is it looks at the FID that is generated by the Tesian polygon and you're going to add that specific attributes to all three of these different data sets. So if you open up the spatial join box, it might take a second, but you'll see how it'll give you an option to select the Cartesian polygon FID and add it specifically to the attribute table of the subject that you're trying to add it to. In this case, our target feature is the point of interest. So we're going to add the FID to the point of interest. We're going to add the FID to parking areas and the Bigfoot sightings. So once that's run, you can see the outputs here is you'll have the FID and you'll have as well as the XY that we added earlier as well. So here's the FID. And then for our points of interest. And why this is important is because how we ran the actual Cartesian polygons earlier is, remember that this is the equal distance in an area based on the parking lots. So if you look at the point of interest, you can see that when they fall into that specific Cartesian polygon, it's going to add it specifically, right? So now that we have that, what's the next part of our analysis? And I did this in its own model because I want to show you how easy it is to add a model within a model, like Kristen was mentioning earlier in her PowerPoint. So we're going to do something and create something called a desire line. Essentially what that is a visualization of going from one point to another in a linear distance. So once this runs, we ran our desire lines for our parking areas and to our Bigfoots and the points of interest. So we'll go parking to our points of interest, and we can quickly zoom in here, where you can see clearly that this parking lot accesses these points easier and closer than any of these parking lots that are also available. And let me show you how it's a drag and drop feature. So here's my analysis model. You drag and drop it in here, and you can add the parameters specifically from the grouping of our spatial join. Now, another thing that you can run is what's called a logical tool, which Kristen mentioned earlier. And in this logic, what we're doing is we want to determine if we're trying to get from one area or another, what is the closest I'm willing to walk, right? So if I don't want to walk more than, say, a mile or a mile and a half, you can say, if this field value is true, then go ahead and make a selection of everything that is over a mile and a half. And you can see all of the selection features here, which you can also do the opposite, where if it's less than or equal to, let's just open this up, where if it's less than or equal to, say, if you don't want to walk more than, say, 5 miles, you can do that same analysis as well. And I'm going to pause here. Kristen's going to talk some about sharing. So Kristen, go ahead and take it away.
All right, so now I know where I need to park in order to beat the crowds. Yes. And whether or not I might have to wake up at 4 a.m. to do that will be a different answer or a different problem to solve. All right, so we're getting into the final stretch here, and we're going to wrap up with some sharing and collaboration. And that's really just focusing on how we can disseminate our content, disseminate and share our workflows, and leverage what other people are producing as workflows. And you can do that in various different manners. And one of those is Python, and another is taking those tools and sharing them as a service. So we also have access to reports, and reports are very important when you're trying to check for accuracy, you're trying to remember what you did. Well, ModelBuilder has that capability. And it shows all the variables and tools in that model, along with each of those elements' values and other properties. The report is categorized in 2 sections. It has variables and it has processes. The tip here is to utilize the auto sync on your reports. So this allows the model edits to be continuously updated within that report. The other, and this is a new feature, so it's a new capability for ArcGIS Pro 2.5. You're able to take your model and export it as a Python script. Another thing is you can export that model as an SVG or a PDF. So we have this standalone model, but we also need to take into account for automation. So you might want that geoprocessing model to run at a specific time of day, or set the model to run repeatedly at some time interval. Maybe the model takes a long time to run and you want the results to be available at a certain time every day. You can schedule the model to run at a particular time and specified frequency using that Windows Task Scheduler. And then just with a few lines of code, you're able to run it there. You're also at ArcGIS Pro 2.5, any geoprocessing tool, including that model tool that we created, can be scheduled within the platform or within the Pro environment. So let's break this down for a Windows Task Scheduler. So here we have our Python code where we're importing that Python, we're importing that toolbox, and then I'm creating a trigger. So this is breaking it down to, I need it to be on a schedule, I need it to run daily at 5, and then I need to create a task and an action that's associated with that. The schedule model is listening in the geoprocessing and the scheduled section of the history pane. The scheduled section will display all the tools that are scheduled to run on the machine using your user account, regardless of the project from which the tools are scheduled. You must be logged into the machine for the scheduled tools to run. Each tool in the scheduled section will include a list of execution history, and then each time that the scheduled tools run, a new timestamp is added to that item. It would also indicate whether it's successfully run or failed. And then you can manage those in a couple of different ways. You can change the schedule options as a date time, recurrence, expiration, etc. There are many geoprocessing tools that allow you to solve diverse spatial problems, perform analysis to transform the raw data into information, and automate your data management. Those value tools can be extended by sharing them as one of the following: a geoprocessing package, which can be uploaded to ArcGIS Online, emailed to others, or shared through your local network, or a web tool, which Jeff is going to show you. So with further ado, I'm going to kick it off to Jeff for our last and final demonstration.
Thank you, Kristen. And I am sharing my screen again. And can you see it? Yes, looks like you can. So one of the first things that I want to show you is how easy it is to export this out as a Python file. So you can export this out as an actual file if you're into PyCharm or Visual Studio or any of those, or you can view it within the actual Python window within ArcGIS Pro. You can edit and you can manipulate any of the features or attributes within the model through this Python window. Another item that Kristen was talking about was scheduling. So if you want to schedule this model to run, like for example, let's say if a whole bunch of new Bigfoots, wind up popping up around the country, you can have this model run to figure out where you should park, specifically in Glacier, in this case, to view those specific Bigfoots. You just click on this down here, schedule it, and then you have all your timing parameters at your fingertips here. Another item I wanted to show you is how easy it is to share this out, either as a geoprocessing service or a web tool. So here's when you click on sharing out as a geoprocessing package, it opens up this pane over here on the right, and you enter all of these parameters. We have this tagging system within your ArcGIS Online or your portal account. Once you package it up and send it out, show you what it looks like. Let me open up my Chrome window here. And in this case, this is our ArcGIS Online account. We'll go to our content page here, and then you'll see that it is available here. And so now that we have this as a geoprocessing tool, you can create a web map, and you can add this exact model as a widget. Here's our geoprocessing widget. Click OK. And this is where you add your parameters and the values for your geoprocessing service to add into your web map. And you can do this through Web App Builder or the JavaScript API. So, and I think that's it, Kristen.
All right, so now you can take all of that analysis and make an interactive application to find and plan your trip out to Glacier National Park once all restrictions are lifted, and we can all go hiking and see bighorn sheep and wolves, and maybe not so much wolves. Maybe just stick with like bald eagles and bighorn sheep and hiking.
And
all right, guys.
And the Bigfoot as well, Kristen. You have to remember
Also Bigfoot. All right, so let me go ahead and share my screen and wrap up for the final portion with some resources here. All right, so just to break this down, we showed some workflows on data cleanup, preparation, search, and entry. We focused on some different ways of doing a spatial analysis. It could be simple, it can be really complex, where you're using machine learning and object detection and big data analytics. And then finally, we get to that sharing and collaboration. So creating those web tools, widgets, and then interacting with our end users. Final resources is that there are so many different educational resources, instructor-led training, books, online help, learn ArcGIS exercises, technical support, not just for bugs. And then you have this gallery of tools that you can download, modify, and utilize within your own analysis. And don't forget, we also have MOOCs. So with that, I thank you. I hope you enjoyed our presentation. Please feel free to reach out to us individually. And then with that, I'll pass it back over to you, Margie.
Great, thanks so much for that excellent presentation. We actually have handled most of the questions. I know Maria has one that we'll follow up with her offline about. But yeah, so I think we're good with questions. So thanks again, Jeff and Kristen. Excellent presentation. And thanks everyone for spending your time with us today. Have a great day.